Hi again. So this is the second part of our review set of videos. Just as a quick reminder, this is not intended to be an in-depth or thoughtful review of these subjects. This is just a surface level topic review to help refresh these ideas in your brain whole. Okay? So we're going through our second unit of ecology here, and let us begin. So the first bullet point that we are going to look at says create or modify energy pyramid models or food chains / webs that incorporate the 10% rule. And so the 10% rule is referring to the way that energy moves through the ecosystem, through consumption. Right? And so when the producers make the energy doing photosynthesis or chemosynthesis, we can think of them as having 100% of that energy since they made it. Right? When the primary consumers eat those producers, they only get 10% of whatever energy was originally available. Right? And now that's a rough estimate. Sometimes it's less, sometimes it's a little bit more, but on the average, it's around 10%. When the secondary consumers eat those primary consumers, they, once again, only get 10% of what was available then, which is to say 1% of the total energy from the get-go. Okay? And then when the tertiary consumers eat the secondary consumers, we lose another 90%, and we're down to 0.1% of the original energy available. Okay? And so there's a vast amount of energy lost as different organisms eat each other. Putting it in number form, if I start with 1,000 kilojoules of energy at the producer level, the primary consumers only get 100 kilojoules, the secondary consumers will only get 10 kilojoules, and then the tertiary consumers will only get 1 kilojoule out of that original 1,000. Right? So most of it is lost. 999 kilojoules were lost through transfer. All right. Same storyline, different format. This is a food web where the producers, again, have 100% of the energy. In this case, I made it 70 kilojoules. Primary consumers get 10% of that original energy, which is to say 7 kilojoules. And then secondary consumers would only get 1% of the energy, which would be 0.7 kilojoules. So these tertiary consumers are going to have to eat a whole lot of primary consumers, and these primary consumers are going to have to eat a whole lot of producers. Right? So by the time we get up to this level, a whole lot of producers are dead. Cool? All right. So our next bullet point asks us to address where did that energy go? Right? So we lost 90% of the energy for each transfer. Right? This bullet point asks to describe how inefficient energy transfer between trophic levels affects the number of organisms at each trophic level, and to develop explanations for why energy metabolism, heat energy loss, and waste result in the reduction of the energy available. Okay? And so let's first talk about the mechanisms. Inefficient transfer of energy. So metabolism, when we are breaking down the food that we eat, that act itself takes energy, right? So there's energy lost there. And a lot of the substances that we are broken down, what would have been energy available to us is actually released as heat from our body. And heat is not functional energy, right? And so that energy is gone to the universe, so we lose it there. When organisms eat other organisms, they don't manage to eat 100% of that organism, right? So if a wolf eats a bunny, there's going to be some bunny scraps left over. Okay? So there's energy lost there. Simple, straightforward. Yeah. And then there's also the fact that that bunny used up a lot of the energy that it got from the plants, right? So when the bunny ate the plants, it used a lot of that energy for its own purposes. And so by the time the wolf eats that bunny, a lot of that energy has already been used up. And so that's where the energy is disappearing to. And what this means is basically the higher you go up in trophic level, the less organisms that trophic level can support, because there's going to be less energy available to it. Right? And so if I have a tertiary consumer, there's going to be less tertiary consumers than there are secondary consumers because there's less energy available for them than there is for them. Okay? This next bullet point shifts us away from energy transfer and into the story of nutrient cycling, and particularly in this case, carbon. So we're looking at the carbon cycle. It asks us to identify the 4 primary forms of carbon in the environment and the regions within the environment that serve as sinks for each. And so a carbon sink is an area that holds a lot of carbon. Can store a lot of carbon. Our main forms of carbon are carbon dioxide, CO2, which is stored in the atmosphere, in the air we breathe, stored primarily in the ocean. There's a lot of CO2 stored in the ocean. Okay? And there's a lot of CO2 stored in large forests. Okay, so these are the sinks for carbon dioxide. Carbon also shows up in a lot of waste, right? So if you think of all the organisms that are pooping all over the world right now, right? There's a ton of poop out there, just poop everywhere. Poop just covering the planet. Right? All that feces is made out of a ton of carbon, right? There's a lot of carbon in that poop. So that poop holds a lot of the carbon in the world, right? A lot of carbon in that poop. The biomass, which is to say the still living things, right? Living things are made primarily out of carbon. Right? So as a human, right, we have a lot of water in our body. I think it's something like 80% of our body is water, but that water is not part of our living structure. Right? The actual living structures that we are made out of are based primarily in carbon. Right? And so we are mostly carbon. And then hydrocarbons. Okay, so if our living things die, we're mostly carbon. Right? Most of the time we're decomposed, right? But sometimes we end up going and being turned into fossils and then getting turned into the sludge that we call oil, right? And so oil is effectively just like long dead things that have been squished by the pressure of the earth. And all those carbons that were in those living things have now been transferred into this oil, into these fossil fuels. Right? And we process fossil fuels into things like gasoline and plastic, and oil and coal and all those things. And all those hydrocarbons have a lot of carbon in them. Okay? Carbons. Continuing with the carbon cycle, okay, we're asked to construct a labeled diagram of the carbon cycle that includes photosynthesis, cellular respiration, decomposition, and combustion. It's 4 things in this diagram. We're also going to use this model to communicate that carbon is moved from CO2, which is inorganic, in the environment, to sugar molecules, which is organic, through the processes of photosynthesis and cellular respiration. So let's take a gander at this model. Here we go, zooming out a little bit. So this is our carbon cycle model. Usually you'll see pictures of like trees and animals and factories and stuff. I've used words because words are cool too. All right. So here in this section, we have our little organic to inorganic cycling. Right? So this is when the carbon stays within living things. So photosynthetic organisms like trees and grass and cyanobacteria utilize CO2. Right? It takes the carbon out of CO2, takes some energy from the sun, and it smashes together those carbons, and some hydrogens and some oxygens to make sugar. So the carbon is now in the sugar. That sugar is broken down by the process of cellular respiration. So those sugars are ripped apart, and then the carbon is released again in the form of CO2. Okay. And so this is one cycle here. It just goes back and forth and back and forth and back and forth. Okay. Now, these are processes done by living things. Okay. And as you may know, you may have figured this out at some point in your life, living things, they die. right? And so when living things die, there's two paths that they can go down. Most things go down the path of decomposition, right? And so a living thing dies, decomposes, come along and break down that living thing back into its base components. Those decomposers extract energy through the process, and then a bunch of gases are released, and one of those gases being CO2, but also like methane and other carbon-based gases. And then those gases make their way back into the environment, and then they recycle through the process. Alternatively, those dead things might end up as fossil fuels, or not even end up as fossil fuels. Sometimes they're just burnt, right? So either they turn into fossil fuels, or they just get straight up burnt. Like if I cut down a tree, I can burn a tree, right? So combustion is effectively the process of burning something. Okay? And so you combust it, you break it down into its components, and energy is released, and we see fire as energy, the heat, the light, that's all energy, right? But also CO2, the carbon is released as gas. And so it makes its way back into the atmosphere to get back into this cycle. Okay? So this is our carbon cycle model. It covers photosynthesis, cellular respiration, decomposition, combustion. Okay? Look at that. We're already at the bottom end of our list of bullet points here. Okay? This one says use models such as basic equations of photosynthesis and cellular respiration to show how carbon atoms cycle through organisms and the environment. So one of the things to keep in mind here is some of our basic laws of the physical world, and that's that matter and energy cannot be created or destroyed, right? It's just passed back and forth between different things. All right. And so the carbon in our system is just moving to different forms, back and forth and back, depending on what stage it's in. And so if we look at the equation here, this is the chemical equation for photosynthesis, right? Let's do this, boom. Over here we have our reactants, which are the things that go into the reaction. And over here we have our products, which are the things that come out. And since we're following carbon, I made it in this pretty color here. So we see that 6 carbons are going in, and lo and behold, 6 carbons come out. Right? So they go in the form of CO2, and they come out as part of the sugar, right? But it's the same amount of carbons. Go in the opposite direction, right? The process of cellular respiration takes that sugar, those 6 carbons, right? Rips apart that sugar, restructures some stuff, releases some energy along the way, and we end up with our 6 carbons coming back out in the form of 6 CO2s. So you can see here that the carbon is just passed back and forth, doesn't get made, doesn't get destroyed, it just gets altered and passed around. That's what makes it a cycle. Okay? And look at that, it's the last bullet point I want to talk about. And these bullet points say, create a model that demonstrates how changing carbon production usage rates in one sphere impacts carbon levels in other spheres. Also analyze and interpret data to explain that increased combustion of fossil fuels has released more carbon dioxide in the environment, resulting in climate change. I'm just going to do the first part of that. Okay? So here I have a tree. Right? This tree, in my imaginary model, has 70 units worth of carbon. When I light that tree on fire and burn it up through combustion, right, that carbon is going to be released primarily as gas, CO2. And that CO2 is escaping into the atmosphere. So let's say that 65 units of carbon are now in the atmosphere. There's also some ash left over from burning the tree. Let's say that has 5 units of carbon. And so by changing the mode of storage, right, from one sphere, the biosphere, here the biomass, right, and I've combusted the biomass and released it into the atmosphere. Right? I still have the same amount of carbon floating around, right, but I've changed where it's at. So I used to have more carbon in the biomass, but now I have more carbon in the atmosphere. Right? That makes sense. I don't really think I have to explore that too deeply. Right? That's just logical. It has to go somewhere, right? So if I remove it from here, it has to go somewhere else. And in this case, that carbon being in the atmosphere is going to do all that greenhouse gas stuff, trap the light in from the sun, make the earth hotter, resulting in climate change, end of the world, we all die. Bye.